good evening, and welcome. If you are hearing this, it is likely that the day is finally done. The lists have been put away, the doors have been locked, the screens have gone dark, and all that is left is the quiet, expansive interval between the work of the world and the work of dreams. This is a protected time, a time when curiosity can take its time. There is nothing to solve here, nothing to win, nothing to prove. There is only the gentle act of turning a question over in the mind, much like one might turn a smooth, heavy stone in the palm of the hand, letting it catch the low light. The air in the room around you is still, holding the memory of the day's warmth or the encroaching coolness of the night. Your breathing is slow and steady, a quiet rhythm that has carried you through everything that has happened and has now brought you to this place of rest. And in this comfortable, encompassing quiet, let's allow a single, elegant question to settle, not as a challenge, but as a gentle companion. What if the story of our world, of Earth, isn't the triumphant story of inevitable success, but one of improbable, nail-biting survival? What if Earth is not the blueprint, but the outlier? What if it is one of many worlds that tried, and the only one nearby that held on? Let's be perfectly and gently clear about what we are doing here tonight. This is not an argument, it is not a debate, nor is it a warning meant to stir unease. Think of it instead as a kind of exploration, a gentle and methodical mapping of a vast and quiet territory of thought. The question of failed worlds is not a judgment on those worlds, but a framing device for our own. It helps us to see our own planet not as the default, the standard model for what a living world should be, but as a particular and perhaps very fragile outcome among a universe of other possibilities. Our lens tonight is one of dedicated inquiry, not of assumed certainty. We will handle ideas carefully with a soft touch, acknowledging precisely where the hard data gives way to reasoned speculation and where our most sophisticated models are just provisional sketches of an immense and complex reality we are only beginning to comprehend. There are no absolute truths waiting for us at the end of this journey, only a richer, more textured, and perhaps more humble perspective. We are simply here to wonder together, to hold a grand idea and feel its weight and shape and temperature without any need to conquer or solve it. The guardrails for our journey are firmly in place. We will move slowly, we will favor questions over answers, and we will honor the magnificent, humbling uncertainty of it all. This is a protected space for methodical curiosity, a place where not knowing is the very beginning of the adventure, not its unfortunate end. And so, we will proceed with a spirit of deep generosity toward all the ideas we encounter, those that comfort and those that challenge, treating each one as a valuable piece of a much larger puzzle we can only ever hope to glimpse. Before we venture out into the vastness of the cosmos, let's first arrive fully, completely, where you are, right now, in this specific moment. Feel the space your body occupies. Notice the gentle, constant pressure of the surface beneath you, the way it supports your weight completely and without effort. You can let go into that support. Become aware of the texture of the fabric against your skin, the subtle map of its weave, the way it holds a particular temperature. The air in the room is not an emptiness, it is a substance. It has a quality you can feel as it enters your body and as it leaves. It touches the skin of your face. Is there a sound in the far distance, the low, steady hum of an unseen appliance, the whisper of wind moving through trees outside, the faint, indistinct murmur of a world settling down for the night? Or is there a profound silence, a quiet so deep you can almost hear the beat of your own heart? These are the sensory anchors of your present moment. This room, this body, this breath, these are concrete things, real and immediate. We begin here because all grand explorations of abstract cosmic ideas are more meaningful and more stable when we know exactly where home is, before we speak of planetary atmospheres and geologic timescales measured in billions of years, we must first honor the simple, profound reality of the air you are breathing now, the quiet and steady rhythm of your own personal life support system. This present tense grounding is our point of origin, the place to which we can always return. It is the solid ground from which we can safely gaze into the magnificent and sometimes dizzying vastness. Why should a question like this even matter? What are the true stakes of wondering about worlds that might have failed? On one level, the timescale of planets is so impossibly immense it can feel entirely separate from the brief flicker of our own lives. The birth, life, and death of a world is a drama played out over eons, a story written in cooling rock and condensing gas, a narrative whose chapters are hundreds of millions of years long. But on another, far more intimate level, the continued stability of our own world is the foundational assumption for everything we are. It is what makes the human timescale possible at all. The reliable, predictable turning of the seasons, the precise and life-sustaining chemistry of our atmosphere, the ever-present miracle of liquid water, these are not givens. They are not simply features of a generic planet. They are the hard-won consequences of a long, contingent, and often violent history. The question matters because it fundamentally reframes our relationship with the ground beneath our feet and the sky above our heads. It shifts our perception of Earth from a static, passive backdrop for human events to a dynamic, ever-changing, and perhaps deeply fragile system. To seriously consider the worlds that didn't make it is to appreciate, with a new and penetrating clarity, the delicate, intricate architecture of the one that did. It connects the slow, deep, silent time of geology with the fleeting, precious time of a single life, a single day, a single moment of quiet, conscious reflection, like this one. It suggests that our existence is predicated on a winning streak of incomprehensible length. As we move forward into the heart of this exploration, we will follow several distinct threads of inquiry. Think of them as paths leading into a great, quiet, twilit forest. We don't need to see their final destination just yet. We only need to know that they are there, waiting to be explored, and that each one offers a different perspective on the same central mystery. One of these paths will lead us to our immediate planetary neighbors, to Mars and Venus, worlds that began with such similar ingredients to our own, but followed radically different and ultimately life-ending trajectories. We will ask what their stories, told in sterile, wind-scoured dust and crushing superheated pressures, might reflect back about the fragility of our own world's success. Another thread will take us deeper into the internal machinery of Earth itself, into the silent planetary-scale conversations between rock, ocean, ice, and air that have, against all odds, kept our world in a delicate, habitable balance for eons. We will examine the gears of this planetary clockwork. And a third, more speculative and philosophical path will invite us to consider the very definition of success and failure on a cosmic scale. Is a world with only microbial life for 3 billion years of failure? Or is that a different kind of success? We will return to each of these threads in their own time, weaving them together as we go. For now, just let them be markers on the horizon, gentle promises of a journey to come. To have a useful and coherent conversation, we need to agree on what some of our key words mean, at least for the duration of our time together tonight. Let's start with a world. For our purposes, this will mean a terrestrial, rocky planet, a body more or less like Earth, Venus, or Mars, existing within the solar system of its parent star. When we use the word failed, we are not making a moral or aesthetic judgment. We are using it in a purely functional, systems-oriented sense. A failed world simply means one that did not sustain the necessary conditions for the emergence and long-term survival of complex, multicellular life over billions of years. A failed world might be one that lost its atmosphere to space, or boiled its oceans away in a runaway greenhouse effect, or, froze solid into a permanent snowball state. It is a world where the window for life, if it ever opened, eventually slammed shut. An essential assumption we will make is that life, at least as we can imagine it and detect it, requires three fundamental things: a stable source of liquid water on its surface, a reliable source of energy like a parent star, and a diverse range of key chemical elements. This is our working model, a necessary simplification that makes our grand question manageable. And finally, let's define habitability. This isn't a simple on or off switch. It is not a binary state. It is a continuum, a spectrum. A planet can be transiently habitable for a few 100 million years, or marginally habitable in small, protected niches, or, like Earth, robustly and continuously habitable across its entire surface for a very, very long time. Our inquiry tonight is about that continuity, about what it takes for a world not just to spark life, but to keep it, to protect it, to allow it to flourish and diversify through all the challenges a cosmos can throw at it. To understand the profound question of other worlds, we must first briefly but properly situate our own. Our planet, Earth, formed about 4.5 billion years ago, coalescing from the same vast, swirling protoplanetary disk of gas and dust that gave birth to our Sun and all the other planets in our solar system. For its first 500 million years or so, a period known as the Hadean Eon, it was a molten, chaotic and utterly hellish place, constantly bombarded by a fusillade of asteroids and comets, the leftover debris from the solar system's construction. But as this violent cosmic rain subsided and the planet cooled, a global ocean of liquid water formed beneath a thick, dense atmosphere. And within that primordial ocean, somehow, against all probability, life began. The earliest widely accepted evidence for life on our planet dates back at least 3.5 billion years, with some more tentative evidence suggesting it may have begun even earlier. For the vast, overwhelming majority of Earth's history, for about 3 billion years, life was purely microbial. The planet was ruled by simple, single-celled organisms. It was only in the last 600 million years that complex, multicellular life exploded in a riot of diversity, an event known as the Cambrian explosion. Throughout this immense, almost incomprehensible span of time, our planet has faced and survived a litany of existential threats, massive, continent-spanning volcanic eruptions that choked the skies with ash, catastrophic asteroid impacts that vaporized oceans, and dramatic, lurching shifts in climate that encased the entire globe in ice. Yet through it all, the planetary system as a whole has always recovered. It has maintained a kind of geological thermostat that, despite wild fluctuations, has always managed to keep the planet's average temperature within the narrow, precious range required for liquid water. This is the grand narrative, the essential context for our inquiry. A story not of placid stability, but of radical persistence through profound, repeated, and often violent change. Let's begin our first major track of evidence with something we can visualize on a human scale. Think of a thermostat in a house. It's a beautifully simple negative feedback mechanism designed to maintain stability. When the temperature in the house drops below a chosen set point, a sensor detects the change and sends a signal to the furnace, which turns on, releasing heat. When the temperature rises above that set point, the furnace turns off. This process, a negative feedback loop, actively counteracts change, maintaining a stable internal environment despite the wild fluctuations of the weather outside. Now let's try to imagine this same fundamental principle operating on a planetary scale over millions of years. Earth has just such a mechanism, a geological thermostat known as the carbonate-silicate cycle. It works with elegant, slow patience. Carbon dioxide in the atmosphere dissolves in droplets of rainwater, forming a very weak solution of carbonic acid. This acid rain falls on the vast, exposed silicate rocks of the continents. Over immense timescales, this acid rain weathers the rocks, breaking them down chemically. This weathering process releases calcium, magnesium, and other ions, which are then washed by rivers into the oceans. In the sunlit layers of the oceans, tiny marine organisms like plankton and corals use these dissolved ingredients along with dissolved carbon to build their intricate shells and skeletons of calcium carbonate. When these organisms die, their shells sink to the deep ocean floor, forming a thick layer of sediment. Over geological time, this sediment is compacted into carbonate rock, like limestone, effectively locking that atmospheric carbon away in the planet's crust. This whole process removes CO2 from the atmosphere, which tends to cool the planet by weakening its greenhouse effect. But what if the planet gets too cold? Colder global temperatures mean less evaporation from the oceans, less rainfall on the continents, and therefore a much slower rate of rock weathering. The geological removal of CO2 from the atmosphere slows to a crawl. Meanwhile, volcanoes, which are driven by the planet's internal heat and are indifferent to the surface temperature, continue to release CO2 at a more or less steady rate. With less CO2 being removed and the same amount being added, the concentration in the atmosphere gradually begins to rise. The greenhouse effect strengthens and the planet warms back up. This planetary scale feedback loop, this geological thermostat, has acted as a crucial, long-term stabilizing force for billions of years. But what happens if a key part of that incredibly slow, patient mechanism breaks? What if the furnace is taken away or the thermostat gets stuck? The existence of a planetary thermostat like the carbonate-silicate cycle has truly profound implications. It strongly suggests that Earth's long-term habitability is not a matter of sheer, dumb luck, of being in just the right place at the right time. It is, instead, the result of an active, dynamic, self-correcting regulatory system. However, this system, like any complex machine, has its limits, its tolerances, and its critical vulnerabilities. Let us consider the boundary cases, the edge conditions where the thermostat might fail. What if a planet is too small, like Mars? A smaller planet has less internal heat to begin with and loses that heat to space much more quickly. Its molten core solidifies, its magnetic field dies, and most importantly for our thermostat, its volcanic activity ceases. Without volcanoes, the crucial input of new CO2 into the atmosphere shuts down. The weathering process, however, continues to remove the remaining CO2, and with no way to replenish it, the atmosphere thins, the greenhouse effect weakens, and the planet freezes into a permanent ice age. The thermostat breaks because its furnace has run out of fuel. Or consider the opposite case. What if a planet is too close to its star, like Venus? The initial surface temperature is so high that its oceans of liquid water begin to rapidly evaporate, filling the atmosphere with water vapor. Water vapor is itself an extremely powerful greenhouse gas, which drives the surface temperature even higher, which in turn causes the oceans to evaporate even faster. This is a runaway positive feedback loop, a vicious cycle. The planet becomes a pressure cooker, a furnace. Eventually, the temperature is so high and the atmosphere so thick that the oceans boil away completely. The water molecules in the upper atmosphere are then broken apart by intense ultraviolet radiation from the star, and the lightweight hydrogen atoms escape into space forever. The planet's water is permanently lost. These are not hypothetical, abstract scenarios. They appear to be the actual histories of our immediate neighbors. This implies that the habitable zone around a star is not just a passive question of distance and incoming sunlight. It is an active, dynamic property that also depends on a planet's geological and, as we shall see, biological capacity to regulate its own climate. The system is robust, but it is not infinitely so. It operates within a specific set of parameters. If a world strays too far outside those parameters, the stabilizing feedbacks can fail, or even worse, can transform into powerful, destabilizing ones. Now for a moment, let's zoom in from these vast planetary systems to the scale of a single, living, breathing system, you. As you listen to this, you are part of a vast, distributed network of systems, and so are countless others in different rooms, different cities, different countries, different time zones, all listening to this same exploration. Take a moment to imagine the sheer, silent number of people participating in this moment, each in their own quiet space, each a unique point of consciousness on the curved surface of this planet. Perhaps you might feel moved to leave a quiet, anonymous comment, noting your location and the time of day, a small digital signal of your presence in this shared, invisible community of curiosity. It serves as a gentle reminder that even our most solitary and internal reflections can be part of a larger, silent conversation. And if this journey is one you wish to continue in the future, a simple, effortless act like subscribing ensures that these explorations can continue as well. But there is absolutely no urgency. The most important thing is to simply be here, now, in this moment of shared, methodical wonder. The rest is secondary. Let's pause our forward momentum and consider, with fairness and intellectual generosity, the most straightforward and powerful objection to our central question. This is the rare Earth hypothesis. In this carefully argued view, Earth is not a resilient survivor among a multitude of failures, but an exceptionally rare jewel, the result of a near-miraculous and perhaps unique confluence of fortunate events. Proponents of this idea, like the paleontologist Peter Ward and the astronomer Donald Brownlee who first proposed it, point to a long and daunting list of factors that had to be just right for complex life to emerge and persist. Earth is in the Goldilocks zone of our solar system, a narrow band of orbital distance where surface temperatures allow for liquid water. It has a large moon, which, as we will explore later, stabilizes our axial tilt, preventing wild, catastrophic climate swings and giving us predictable seasons. We have a strong, protective magnetic field generated by the convection of our molten iron core, which shields the surface from the sterilizing effects of the solar wind and cosmic radiation. We have the engine of plate tectonics, which not only drives the geological thermostat we just discussed, but also recycles essential nutrients and promotes biodiversity by creating new habitats. Our solar system has giant planets like Jupiter and Saturn in stable, nearly circular outer orbits. These gas giants act as crucial cosmic bodyguards, gravitationally ejecting or absorbing many of the asteroids and comets that could otherwise cause devastating, extinction-level impacts on the inner planets. The list goes on and on, from the right kind of star, a stable, long-lived G-type star, to the right position in the galaxy, the galactic habitable zone, far from the intense radiation of the galactic core, to the right amount of water. From this perspective, the reason we don't see other successful worlds teeming with complex life is not because they all failed, but because the conditions for success are so extraordinarily, prohibitively difficult to achieve in the very first place. Earth isn't the one that got lucky. It's the one that won an unbelievable cosmic lottery, a lottery with odds of billions to 1. Now let's lay another interpretation directly alongside that one, not as a direct rebuttal, but as a profoundly different way of seeing the same set of evidence. This is the mediocrity principle, which is a modern extension of the Copernican idea that we are not in a special or privileged position in the universe. This principle suggests that if something happened here on Earth, given the vastness of the cosmos, it has likely happened elsewhere countless times. In this view, the fundamental ingredients for life are common, even ubiquitous, throughout the universe. Rocky planets orbiting within the habitable zones of their parent stars are now known, thanks to missions like the Kepler Space Telescope, to be incredibly plentiful. Water is one of the most abundant molecules in the cosmos. The complex organic molecules that serve as the chemical building blocks of life are found in meteorites, comets, and even in the cold, dark clouds of interstellar gas. From this perspective, the central question is not why Earth succeeded, but why so many others, which should have had the same starting materials, might have failed. Perhaps life itself, the initial spark of biology, is not the rare thing at all. Perhaps the great bottleneck is not the origin of life, but its long-term persistence. In this model, the galaxy might be filled with planets that had life for a time, perhaps for 1 billion years, perhaps just for a few million, before one of their key planetary regulatory systems failed, or they were hit by a sterilizing impact, or their star became unstable. They are not rare Earths, but failed Earths. The universe, in this slightly more melancholic telling, is not an empty, sterile desert. It is a cosmic graveyard filled with the ghosts of biospheres that flickered into existence for a time and then, for one reason or another, died out. How do we actually know what we know about any of this? Our knowledge of other worlds, both within our solar system and beyond, is gathered through instruments of incredible, almost magical sensitivity. But these instruments also have inherent and profound limitations. We study the atmospheres of distant exoplanets, worlds orbiting other stars, by analyzing the faint, filtered light of their parent star as it passes through that atmosphere on its way to our telescopes. This technique, called transit spectroscopy, can tell us about the presence of certain gases like water vapor or methane, but it's a blurry, averaged signal from an entire world, a single pixel of light. We study the history of Mars by sending robotic rovers to analyze the chemistry and geology of rocks in a few specific, carefully chosen locations. And from these tiny samples, we attempt to extrapolate the story of an entire planet over billions of years. There is a profound and unavoidable survivorship bias at play in all of this. We study one living, breathing, successful world, our own, in exquisite microscopic detail, and we compare it to a handful of nearby worlds where life is either clearly absent or, at best, deeply hidden from our view. We are like detectives arriving at a complex scene with only one loquacious survivor and several silent, uncommunicative victims. The survivor's story is compelling, detailed, and coherent, but is it the only story that could possibly have been told? We must constantly and rigorously ask ourselves what we are not seeing, what evidence has been erased by 4 billion years of geological churning, atmospheric loss, and cosmic radiation. Our methods are a stunning testament to human ingenuity and persistence, but they also define the precise boundaries of our understanding. The main thread of our inquiry tonight depends entirely on what these methods can, and more importantly, cannot detect. The very language we use to discuss these immense systems shapes the way we think about the problem. When we speak of a planet regulating its climate or a biological system failing, we are using powerful metaphors borrowed from the human-scale worlds of biology and engineering. These are useful, perhaps even necessary, for our understanding, but they carry with them the subtle, smuggled baggage of intent, purpose, and consciousness. A planet does not try to stay habitable. A feedback loop does not want to maintain stability. A species does not decide to adapt. These are emergent properties of complex chemical and physical interactions governed by the fundamental laws of nature. It is crucial for the clarity of our thinking to try to replace these anthropomorphic, purpose-laden verbs with more neutral, mechanical ones. The carbonate-silicate cycle does not act as a thermostat out of a desire for stability. Rather, its rate is sensitive to temperature in a way that produces a stabilizing or negative feedback. This might seem like a small semantic distinction, but it's a critical one for maintaining intellectual discipline. It helps us to avoid the pervasive and seductive trap of seeing purpose or design where there may only be physics and chemistry unfolding over immense stretches of time. Our metaphors are indispensable tools for understanding, but we must always remember that they are not the thing itself. The map is not the territory. Clarifying the inherent limits of these metaphors is essential to keeping our inquiry clear, disciplined, and free of unwarranted assumptions. Let's walk through a hypothetical case study to make these abstract ideas more concrete, more tangible. Imagine you are standing on the surface of a young, promising planet, Let's call it Planet A. It is, for all intents and purposes, an early Earth twin. It is Earth-like in size and mass and is situated at a similar distance from a similar, stable star. It has vast oceans of liquid water and a primitive atmosphere rich in carbon dioxide and nitrogen, which is steadily replenished by a global network of active volcanoes. The geological thermostat we discussed, the carbonate-silicate cycle, is operating smoothly. Rain weathers the rocks, carbon is steadily sequestered and buried in the ocean floor, and the planet's average temperature is kept in a stable, life-friendly range. Simple, single-celled life emerges in the sunlit waters of its oceans. For 1 billion years, maybe even 2, things proceed much as they did on early Earth. The system is stable, the biosphere is slowly growing, but Planet A has a subtle, hidden flaw. It is just a little bit too small, its total mass just a few % less than Earth's. This means its internal heat engine, the radioactive decay in its core and mantle, is less robust and cools more quickly. Over the course of its 3rd billion years, its core begins to solidify. Convection in the liquid outer core ceases, and as a result, its protective magnetic field weakens and eventually dies completely. Without this magnetic shield, the solar wind, the constant stream of charged particles from its star, begins to erode the atmosphere, stripping it away molecule by molecule into the vacuum of space. As the atmospheric pressure drops, the oceans begin to boil away at a lower temperature. The planet's surface is sterilized by a torrent of unfiltered cosmic radiation. The geological thermostat is still theoretically present, the rocks are still there, but it no longer has a substantial atmosphere to regulate. Planet A slowly, inexorably, becomes a cold, arid, rust-colored desert. It has failed. Now let's consider another world, a different kind of failure. Let's call it Planet B. This planet is an even better twin for Earth. It is almost identical in every important way: size, mass, composition, distance from its star. It even has a large moon to stabilize its axis and give it gentle, predictable seasons. Like Planet A, it develops oceans and a primitive atmosphere, and its geological thermostat is functioning perfectly. Life emerges and begins to thrive in its oceans, but Planet B finds itself in a different, more violent kind of solar system. Its version of Jupiter, a massive gas giant, is not in a stable, distant, nearly circular orbit. Instead, its orbit is highly eccentric, and over the course of hundreds of millions of years, it begins to slowly migrate inward toward its star. As this massive planet plows through the solar system, its immense gravity acts like a catastrophic gravitational slingshot, disrupting the orbits of everything around it. It flings a storm of asteroids and comets from the outer reaches of the system down toward the inner planets. Planet B is subjected to a relentless, heavy bombardment of catastrophic impacts, far more intense and prolonged than the one that early Earth experienced. Each major impact event vaporizes a significant portion of the oceans and throws vast, choking clouds of dust and rock into the atmosphere, creating impact winters that last for thousands of years and block out the sun. The fledgling biosphere is repeatedly, brutally sterilized. The conditions for life are constantly reset to zero. The planet's own internal systems are perfectly capable of maintaining habitability, but the external environment is simply too violent, too chaotic. Planet B is not undone by a failure of its own internal machinery, but by the unfortunate lethal dynamics of its cosmic neighborhood. It too becomes a failed world, a battered, lifeless rock. Let's pull our focus back from these hypothetical cases and look at a larger system of interaction, one that was absolutely crucial for Earth's own long-term success: the deep gravitational relationship between a planet and its moon. Earth's moon is, by planetary standards, unusually large relative to the planet it orbits. Most planetary scientists now believe it formed from the hot, spinning debris of a cataclysmic, world-shattering collision between the very early Earth and a Mars-sized protoplanet named Theia. This violent, chaotic birth had a profound, lasting, and deeply stabilizing consequence. The Moon's significant gravitational pull on Earth acts like a steadying hand on a spinning top. Earth's axis of rotation is tilted at about 23.5 degrees relative to its orbital plane, which is what gives us our seasons. Without the Moon's constant gravitational influence, the much smaller gravitational nudges from the other planets in our solar system, especially the giant Jupiter, would cause this axial tilt, or obliquity, to vary chaotically over millions of years. Models suggest it could swing wildly from near 0 degrees, where seasons would vanish, to as much as 85 degrees, where the planet would be tipped over on its side. The climatic consequences would be absolutely dramatic. At high tilt, the poles would receive more direct sunlight than the equator, leading to extreme, unpredictable, and globally disruptive climate swings. The Moon's presence damps these potentially wild oscillations, keeping our planet's axial tilt, and therefore its climate and seasons, relatively stable over geological time. This subtle, silent process of rotational damping through tidal friction is a critical, and perhaps rare, piece of Earth's deep habitability puzzle. The implications of this intimate planet-Moon coupling are almost impossible to overstate. A stable axial tilt means a stable, predictable climate over the long term. Stable, predictable seasons are what allow complex, long-lived ecosystems, like forests and reefs, to develop and adapt. They allow for the slow, patient, iterative work of evolution to proceed without being constantly and catastrophically reset by wild, unpredictable climate shifts. The presence of a large, stabilizing Moon, therefore, might be another key and perhaps rare parameter for long-term planetary habitability. If the specific type of giant impact that formed our Moon is a very rare type of cosmic event, then worlds with stable, predictable climates might also be very rare. This translates the abstract, celestial mechanics of tidal friction and rotational damping into the lived experience of time on a planet's surface. A world without this gravitational stability might be one where the very concepts of summer and winter are meaningless over geological time, a world where the climate of a given region could swing from tropical to Arctic and back again over the course of just a few million years. It is a world where the environmental foundations are constantly shifting, making it incredibly difficult for complex, specialized life to ever gain a permanent foothold. The quiet, steady, reassuring presence of the Moon in our night sky is a constant, silent reminder of this deep, ancient, and profoundly stabilizing partnership. Let's consider another, completely different way that a planet remembers its own long and complex history. Imagine the deep, dark, cold floor of the open ocean. A slow, gentle, and unceasing rain of sediment accumulates there, layer by microscopic layer, over millions and millions of years. Each layer, like a page in a book, captures a detailed chemical snapshot of the ocean and the atmosphere at that specific time. Trapped within these sediments are the fossilized, calcium carbonate shells of countless tiny organisms, the faint chemical traces of ancient metabolisms, and the isotopic signatures of the global climate. The great ice sheets of our planet, like those in Antarctica and Greenland, create a similar but much higher resolution archive. Each year's snowfall is compressed by the weight of subsequent years into a new, distinct layer of ice, trapping tiny, pristine bubbles of the ancient atmosphere. By drilling deep, miles deep into these geological archives, scientists can physically retrieve and read the planet's history. They can analyze the CO2 levels, temperatures, and atmospheric dust from hundreds of thousands, even millions of years ago. These are Earth's memory banks. They are archives of deep time. They reveal the planet's natural rhythms, its great cycles of ice ages and warm interglacial periods. They show us, with empirical data, how the system has responded to past shocks like massive volcanic eruptions or subtle periodic changes in Earth's orbit known as Milankovitch cycles. These records are, by their nature, lagging indicators. They tell us with great precision what has already happened. They are the planet's own meticulously kept chronicle of its long and complex journey. What can we infer, what can we learn from these extraordinarily detailed natural archives? The first and most important lesson is that Earth's climate system is highly sensitive. It responds, and sometimes responds dramatically, to what scientists call forcings, whether that's a change in the sun's energy output, a subtle shift in the planet's orbit, or a change in the chemical composition of the atmosphere. The second critical lesson is that the system contains powerful tipping points. It can exist in multiple distinct stable states, like a glacial period or an interglacial one, and it can shift between these states with astonishing, almost terrifying speed once a certain threshold is crossed. The ice core records from Greenland, for example, show multiple instances of abrupt climate change, moments where the average temperature in the North Atlantic region changed by several degrees Celsius in the span of just a few decades. This tells us that the planet's history is not one of slow, gentle, gradual change. It is a history of long periods of relative stability punctuated by very rapid, sometimes violent transitions. These archives provide crucial, hard-won constraints on our models of planetary behavior. They ground our abstract theories in cold, hard, physical evidence. They show us the operational boundaries of the system's resilience, the absolute limits of its stability. They provide a confidence band for our understanding, reminding us of what we know, and just as importantly, what we still don't know about the intricate, delicate, and sometimes chaotic dance of Earth's climate. We have now looked at several individual complex systems in some detail: the slow, patient work of the planetary thermostat, the violent chaos of external impacts, the quiet, stabilizing gravitational influence of a large moon, and the deep, layered memory of geological and ice archives. Soon we will begin the important work of synthesis, of seeing how these disparate systems connect, interact, and influence one another. We will move from looking at the individual instruments in the orchestra, the strings, the brass, the percussion, to hearing the grand, complex symphony they produce when they play together. We are approaching a crucial midpoint in our journey tonight, a place where we can begin to weave these separate evidence tracks into a more cohesive, more holistic, though still acknowledgedly incomplete, picture of what long-term planetary habitability truly requires. This section serves as a bridge, a gentle promise that we will return to these threads and see how they form a larger, more intricate pattern, a deeper and more satisfying understanding of what it really takes for a world to survive for billions of years. The curiosity we've patiently cultivated so far will be the firm foundation for the synthesis that is to come. Let's turn our attention now to another critical and fascinating feedback system, this time one that is driven not by geology, but by life itself. Think of a vast, continent-spanning forest like the Amazon. The billions of trees in this forest are not merely passive inhabitants of their environment. They are active, powerful shapers of it. Through a process called transpiration, they draw water up from the soil through their roots and release enormous invisible quantities of water vapor into the atmosphere through tiny pores in their leaves. This mass of water vapor helps to seed the formation of clouds directly above the forest. These clouds, in turn, do two crucial things. They reflect a portion of the incoming sunlight back into space, which has a significant cooling effect on the region. And they produce abundant rain, which the forest needs to survive and thrive. The forest, in a very real, tangible sense, creates its own weather. It is a self-sustaining system. This is a classic biome-to-atmosphere feedback loop. Similar, though less dramatic, conversations happen all over the planet. In the vast, sunlit expanses of the open oceans, countless trillions of phytoplankton, microscopic marine algae, produce a chemical called dimethyl sulfide, or DMS. When this chemical is released and enters the atmosphere, its aerosol particles help to seed the formation of clouds over the featureless ocean. More phytoplankton means more DMS, which means more clouds, which means less direct sunlight reaching the ocean's surface, which in turn affects the temperature and growth conditions for the phytoplankton. Life is not just a passenger on planet Earth, passively adapting to whatever conditions it encounters. It is a powerful geological and atmospheric force in its own right. It is woven directly and deeply into the planet's core regulatory machinery. What are the implications of life being an active, powerful participant in planetary regulation? On the one hand, it means that the biosphere can significantly enhance a planet's resilience. It can create entirely new, stabilizing feedback loops like the ones involving forests and phytoplankton that help to keep the global climate in a habitable range. It can, in effect, reinforce the stability provided by the geological systems. However, it also introduces a whole new suite of potential vulnerabilities. These complex, biologically mediated feedback loops have thresholds. A rainforest can create its own rain, but only up to a point. If a region becomes too dry for a prolonged period due to a large-scale external climate shift, the forest can begin to die back. Once a significant portion of it is gone, the rainfall it once generated is also gone, making it much harder for the remaining forest to survive and nearly impossible for it to return. The system can tip, and tip rapidly, into a new, stable, but much less biologically productive state, a savanna or even a desert. This is the logic of tipping points, a concept we saw in the ice core records, but applied here to living systems. The resilience of these intricate biome-atmosphere conversations is not infinite. They are susceptible to shocks. The failure of a key biological feedback loop, a green death cascade, could, in principle, contribute significantly to a planet's overall failure to remain habitable. This adds another profound layer of complexity to our story, one where the long-term fate of a world is tied not just to the stability of its geology, but also to the intricate, adaptive, and sometimes fragile dance of its biology. We can try to understand the nature of life, especially at the deep, informational level of its genetic code, by using a careful analogy. This is a delicate operation, as all analogies are imperfect, so we must be explicit and mindful about the caveats. Think of the genetic code of any organism, from a bacterium to a blue whale, as a form of incredibly complex software, a detailed set of instructions for building and operating a living machine. The cell is the hardware that this software runs on. The external environment is the operating system, providing the necessary inputs, energy, and context. In this analogy, the process of evolution is a slow, patient, iterative process of debugging and rewriting that code over millions of generations. The goal, and we use that word with extreme caution, is not to write perfect, elegant, flawless code. It is simply to write code that is good enough to build a machine that can survive and reproduce successfully in a given operating system. There is no top-down designer, no intelligent programmer. It is a purely bottom-up process of random variation and environmental selection. The caveat here is absolutely crucial. This is only a metaphor. Life is not literally code, and evolution is not literally programming. There is no programmer and there is no intent, but the analogy can be a useful tool for thinking about how biological systems manage immense complexity and respond to disruption. It helps us frame the process in terms of information, feedback, and resilience without ascribing the baggage of consciousness or purpose to it. Viewing biology through this conceptual lens of good enough code helps us to understand the true nature of biological resilience. A well-designed software system, for example, is not one that never encounters errors or unexpected inputs, but one that can handle those errors gracefully without crashing the entire system. Similarly, living systems are not perfect, but they are incredibly, astonishingly robust. They have built-in redundancies at every level. They have sophisticated mechanisms for cellular and genetic repair. They have the capacity to adapt, both individually and as populations, to changing environmental conditions. The 4-billion-year history of life on Earth is not a story of flawless, uninterrupted performance. It is a story of adaptive, messy, and ultimately successful resilience. Entire ecosystems and up to 95% of all species have failed in mass extinction events, but the underlying system of life itself has always persisted. This fundamentally reframes our idea of success. Success in a biological or planetary sense is not about achieving some perfect, static, optimized state. It is about having the flexibility, the diversity, and the robustness to persist through profound change and repeated disruption. A world that fails might be one where its biology, for whatever reason, loses this deep, adaptive capacity. Perhaps the environmental changes it faces are simply too rapid for evolution to keep pace. Perhaps the genetic toolkit of its organisms is too limited. The system becomes brittle, and a shock that it might have otherwise survived, a change in atmospheric chemistry, a nearby supernova, becomes a final, fatal blow. Let's travel back in time once more to a world that is both our own and profoundly alien. 300 million years ago, during the late Paleozoic and early Mesozoic eras, all of Earth's major landmasses were drifting inexorably together, colliding in a slow-motion crash of continents to assemble into a single, immense supercontinent that geologists call Pangaea. Imagine trying to stand in the center of this incredible landmass. The nearest ocean is thousands of kilometers away in every direction. The sky is a vast, empty, burnished copper bowl, almost entirely devoid of clouds. The climate is brutally, unimaginably harsh and extreme. In the long summer, daytime temperatures are scorchingly hot. In the winter, they are bitterly cold. There are no great, lush, continent-spanning forests here. The interior is a vast desert, perhaps the largest the world has ever known, populated only by the hardiest, most drought-resistant plants and animals. The sheer, overwhelming size of the landmass prevents moisture from the oceans from penetrating deep into the interior, creating a continental-scale rain shadow. This was a world of epic, continent-spanning monsoons at its coasts and profound, deathly dryness at its heart. Rebuilding this unfamiliar, alien world in our minds helps us to appreciate how dramatically Earth's own environment, its own state of habitability, has changed over the course of deep time. It was the same planet with the same sun and the same moon, but for 100 million years it was a very, very different world. The existence of supercontinents and the recurring geological cycle of their assembly and breakup has profound and unavoidable consequences for a planet's climate and biology. The vast, arid interiors of a landmass like Pangaea would be deeply inhospitable to much of the life that thrives on our modern, fragmented, ocean-moderated continents. The severe lack of moisture transport limits the extent of forests and wetlands, which in turn has a major impact on the global climate by altering the planet's albedo, how much sunlight is absorbed by dark forests versus reflected by bright deserts. The assembly and eventual breakup of supercontinents is a recurring rhythmic cycle in Earth's history, driven by the slow, powerful dance of plate tectonics. Each phase of this cycle, which lasts for hundreds of millions of years, creates a fundamentally different world, with a different global climate and a different set of challenges and opportunities for life. This implies that even a geologically active, well-regulated planet like Earth might go through long, extended periods where its overall habitability is significantly stressed, where large portions of its surface are much less hospitable to life than they are today. The ultimate success of a planet, then, might depend on its biosphere's ability to weather these cyclical, long-lasting extremes, to maintain pockets of life, or refugia, that can survive the harsh supercontinent times and then expand and diversify again when the continents rift apart and conditions improve. It is another filter, another long and difficult test of resilience. It is only fair, and indeed necessary in an exploration as speculative as this, to turn the powerful lens of skepticism back on our own central premise. What are the strongest, most coherent criticisms of the idea that Earth is a lucky survivor among a galactic graveyard of failed worlds? The most potent and undeniable objection is that we are working from a sample size of exactly one. We have precisely one example of a planet that we know for certain developed and sustained a complex, intelligent, technological biosphere. To generalize from this single, unique data point to the entire galaxy of billions of planets is, from a statistical standpoint, deeply suspect. It is like pulling one single, ornate, blue and green marble from a bag containing 1 trillion other marbles and confidently declaring that all marbles are therefore ornate and blue and green. Furthermore, the argument could be made, and made strongly, that we are fundamentally underestimating the sheer, mind-boggling scale of the numbers involved, the number of planets and the immense span of cosmic time. Given hundreds of billions of galaxies, each containing hundreds of billions of stars, even an exceptionally rare and improbable sequence of events, like the one that led to us, might have occurred many times over. We may not be alone, just profoundly isolated by the vast distances of interstellar space. And finally, as a matter of good scientific practice, we must ask, what are the potential falsifiers for our hypothesis? What discovery could prove it wrong? If the next generation of space telescopes, like the James Webb Space Telescope's successors, were to find clear and unambiguous biosignatures, the chemical fingerprints of life, in the atmospheres of dozens of nearby rocky planets, the failed worlds idea would be significantly weakened. If we were to find definitive evidence of a currently thriving complex biosphere on Mars, or in the subsurface oceans of Jupiter's moon Europa, or Saturn's moon Enceladus, it would be overturned completely. Acknowledging these powerful criticisms and potential falsifiers is not a weakness of our inquiry, but its greatest strength. It keeps us honest, humble, and tethered to the principles of good science. Let's pause our main inquiry again for a brief meta-method interlude, a moment to reflect on how we are thinking about this problem. Think of the work we are doing tonight as a kind of deep-time forensic investigation or a form of cosmic archaeology. The evidence is sparse, often circumstantial, buried in deep, confounding layers, and frequently ambiguous. We have some geological and atmospheric layers from Mars, the data sent back by our robotic rovers and orbiters. We have some tantalizing atmospheric layers from Venus, the information gathered by a handful of probes that survived for a few brief moments on its surface. And we have an incredibly rich, complex, but perhaps dangerously atypical set of layers from our own planet, Earth. Our job is to be like a detective faced with multiple, partially erased crime scenes. We must be constantly aware of our own priors, the intellectual baggage, and the built-in assumptions we bring to the investigation. The rare Earth hypothesis is one such prior. The mediocrity principle is another. When we encounter an anomaly, a piece of data that doesn't fit neatly into our preferred model, we must treat it as a vital clue, not as an inconvenient nuisance. Why does Venus have such a crushingly thick atmosphere, while Mars has almost none? Why did Earth develop a long-lived system of plate tectonics in a way that our neighbors apparently did not? These anomalies are the engines of curiosity and the drivers of new discoveries. We must also constantly account for the problem of erasure. What crucial evidence has been destroyed forever by 4.5 billion years of geological activity, by relentless erosion from solar wind, by the sterilizing blast of impacts? Our conclusions, therefore, must always be provisional, held lightly, built on a foundation of acknowledged and respected incomplete knowledge, and with that essential humility firmly in place, we can now reopen the main thread of our investigation. After soaring through billions of years of deep time and across the vast, empty distances of the solar system, let's bring the scale of our focus back, all the way back, to the intimate, immediate reality of the human body in a quiet room. Feel your own breath, the gentle, autonomous rise and fall of your chest. This is a system. This is a feedback loop in action. Your brainstem, a primitive and ancient part of your brain, constantly monitors the level of carbon dioxide in your blood. When that level rises even slightly, a signal is sent to your diaphragm to contract. You inhale, oxygen enters your lungs and is transferred to your blood, carbon dioxide is transferred out. The level in your blood is restored to its optimal set point. You don't have to think about it. You don't have to will it to happen. It is an autonomous, self-regulating process that works tirelessly to keep your internal chemical environment stable. This is homeostasis, the same fundamental principle of dynamic, self-correcting regulation that we see in the planet's climate system, just operating on a vastly different and more immediate scale. You are a living, breathing, walking example of a successful, complex, resilient system. Grounding ourselves in this embodied reality, this direct, personal experience of regulation and stability, gives us an intuitive, felt sense for the larger, more abstract, planetary processes we are exploring. It connects the abstract idea of a planetary system to the concrete, undeniable reality of your own aliveness. It reminds you that you are not separate from these systems, but a perfect, small-scale expression of them. Let's now turn our attention to one of the most fundamental and non-negotiable constraints on any planetary system: its energy budget. A planet, like any physical object in the universe, is constantly engaged in an energy exchange with its environment. It is constantly receiving a massive amount of energy from its star in the form of shortwave radiation, or sunlight. At the same time, it is constantly radiating energy back into the cold vacuum of space in the form of long-wave radiation, or heat. For a planet's average global temperature to be stable over time, these two immense energy flows, the incoming and the outgoing, must be in balance. Any factor that changes this delicate balance will inevitably change the planet's climate. The intrinsic brightness, or luminosity, of the parent star is one major parameter. The planet's distance from that star is another. A third, critically important variable is the planet's albedo, its overall reflectivity. A world covered in bright white ice reflects more of the incoming sunlight and will therefore be colder than a world covered in dark, absorbent rock or ocean. A fourth, and for us, crucial parameter is the chemical composition of the planet's atmosphere. Greenhouse gases like carbon dioxide, water vapor, and methane act like an invisible, insulating blanket. They are transparent to the incoming visible light from the sun, but partially opaque to the outgoing infrared heat from the surface, trapping some of that heat and warming the planet. These are the primary knobs on the planetary control panel. The complex dynamic interplay between these factors determines a planet's baseline equilibrium temperature. Thinking in terms of these energy budgets allows us to move beyond a simple, static, right-distance model of habitability and see it instead as a complex, multivariable equation, a dynamic balancing act. The energy budget framework is not just a descriptive tool. It allows us to perform a kind of sensitivity analysis. If we reach out and turn one of these imaginary knobs, what happens to the entire system? For example, we know from our understanding of stellar evolution that stars like our Sun get brighter and hotter as they age. Over the last 4 billion years, our Sun's luminosity has increased by about 30%. All else being equal, this steady increase in incoming solar energy should have made the Earth progressively hotter, eventually boiling our oceans and turning our world into another Venus. But the geological record, the archives we discussed earlier, shows with high confidence that Earth's average temperature has remained remarkably stable and has even cooled at times. Why? Because another knob was being turned simultaneously in the opposite direction. Over the same vast span of geological time, the concentration of the greenhouse gas carbon dioxide in the atmosphere has gradually but persistently decreased, reducing the strength of the atmospheric blanket and neatly compensating for the increasing brightness of the sun. This compensation was not a conscious act of planetary management, but an emergent, fortunate property of the carbonate-silicate cycle, which was itself aided by the evolution of life and the subsequent burial of massive amounts of organic carbon in the form of coal, oil, and gas. This reveals the possibility of multiple plausible mechanisms for maintaining stability. A planet might survive a brightening star by systematically reducing its greenhouse gases, or perhaps by increasing its global albedo. It also highlights the critical trade-offs. A planet with a less effective CO2 removal system, or one without active plate tectonics to bury carbon, might not be able to cope with a brightening star. This gives us a much more nuanced view, one where long-term habitability is the result of a dynamic, precarious, and multifaceted balancing act, managed by an array of interacting feedback loops, each with its own sensitivities, response times, and potential points of failure. Long before we had the tools of science to build detailed models of planetary systems, humans were mapping and trying to understand similar patterns of stability, collapse, and renewal through the language of stories, myths, and cosmology. Many ancient cultures from all over the world told stories of a primordial time of balance, a garden, a golden age, a dream time, which was then followed by a profound disruption, a great flood, a world-consuming fire, a long and bitter winter that throws the world into chaos and disarray. This is often, in turn, followed by a period of renewal, the creation of a new world on the ashes of the old one. These powerful narratives can be seen as a form of cultural mapping, a way of understanding the world not just as a static, unchanging place, but as a dynamic, cyclical system with different potential states. These stories often encode a deep, intuitive understanding of interdependence, the idea that the health of the land, the sky, the animals, and the human community are all inextricably connected. We can make a modest but important claim here. These older narratives are not pre-scientific, failed attempts to do geology or climatology. They are a different way of knowing, a different, more metaphorical language for describing the same fundamental patterns of resilience, fragility, and cyclicality that we now explore with the precise tools of systems science. They are a bridge between the observed physical world and the felt internal meaning of living within it. We have now examined with patience and care evidence from the disparate fields of geology, biology, astronomy, and even the cultural lens of mythology. We have seen how planetary systems appear to be governed by a complex web of feedback loops, constrained by fundamental energy budgets and subject to both internal and external shocks. We've looked at the quiet, stabilizing influence of our large moon and the potentially chaotic influence of migrating gas giants. We've considered the crucial role of life itself as both a powerful stabilizing force and a potential source of catastrophic destabilization. We have laid out, as fairly as possible, the case for a rare Earth and the counter case for a universe full of failed worlds. Now we are approaching a significant turn in our journey. The next step is to move beyond these seemingly competing explanations and see if we can integrate their most powerful elements into a wider, more encompassing, and more nuanced model. We are about to tee up a fundamental reframing, a way of thinking that allows us to hold both the undeniable rarity of Earth's specific historical path and the potential commonness of life's humble beginnings in a single, coherent, and satisfying thought. The essential turn we are making is a deliberate shift away from a restrictive binary. The question, it turns out, is not is Earth rare or are failed worlds common? The reframe invites us to seriously consider that both statements might be true simultaneously. Perhaps the initial conditions for life are, as the mediocrity principle suggests, incredibly common. Perhaps simple, single-celled microbial life gets started on billions and billions of planets across our galaxy. This is the common part of the equation. But perhaps, and this is the crucial addition, the long-term persistence of a complex, multicellular, and eventually intelligent biosphere requires a planet to successfully navigate a long and perilous sequence of planetary-scale challenges. This is the idea of the Great Filter, a series of tests or hurdles that most worlds fail to pass. This is the rare part. In this unified view, Success and failure are not two distinct, mutually exclusive categories of worlds. They are simply the two extreme ends of a vast, unbroken continuum of habitability. There might be worlds that are habitable for 100 million years before their core cools. There might be worlds that support microbial life for 2 billion years before their star becomes unstable. And there might be a very, very few, like Earth, that manage to remain continuously habitable for over 4 billion years and counting. The critical question then becomes not why did Earth succeed, but what were the specific, sequential filters that Earth managed to pass through which most other worlds did not. This reframes the problem from a simple, unhelpful, either-or choice to a more nuanced and productive exploration of probability, contingency, and planetary history. It translates the abstract cosmic question into a series of lived choices for a planetary system, a sequence of critical, path-dependent junctures where a world can either stabilize and continue or spiral out of control and fail. Let's begin the work of synthesis. Drawing on all the threads we've explored, we can now attempt to build a minimal provisional model of what long-term planetary habitability seems to require. A successful world, one that stays habitable for the billions of years necessary for complex life to evolve, seems to need several key things to fall into place. First, it needs the right starting conditions, the right raw materials, the right amount of water, and an orbital location in the Goldilocks zone of a stable, long-lived star. This is the essential foundation. Second, it needs a robust, long-lived internal heat engine. This is the driver of planetary life. It powers plate tectonics, which in turn drives the geological thermostat, and it generates a protective magnetic field to shield the atmosphere. This is the engine of long-term stability. Third, it seems to benefit enormously from a relatively stable and calm external environment. This includes the rotational axis stability provided by a large moon and the good fortune of being in a solar system where giant planets are in distant, well-behaved orbits that don't disrupt the inner system. This is the gift of a calm cosmic neighborhood. Fourth, and perhaps most subtly, it needs life itself to become deeply and constructively integrated into its global geochemical cycles, creating new, biologically mediated feedback loops that enhance the planet's overall resilience and adaptability. This is the crucial synergistic integration of geology and biology. Our minimal model suggests that a planet's ultimate success is not due to a single magic ingredient, but to the complex, synergistic, and perhaps highly improbable interaction of all these systems, operating across a vast range of scales, from the churning of the planetary core to the metabolism of a single cell. With this synthesized model in hand, we have an intellectual and ethical responsibility to reconcile the counterpoints and to explicitly and humbly name our remaining uncertainties. The single biggest unknown, the variable that haunts every aspect of this question, is the true probability of each of these factors. We simply do not know how common it is for a planet of Earth's size to have long-lived plate tectonics. We do not know the precise statistics of the specific type of giant impact that is thought to form large moons. We have no idea how often life, once it gets started, successfully manages to integrate itself into planetary-scale geochemistry in a stabilizing rather than a destabilizing way. Each of these is a crucial variable in our grand equation for which we have only one solid, unambiguous data point: our own existence. What remains completely unknown is the true shape of the probability distribution for each factor. Are these all incredibly unlikely, making Earth a true cosmic anomaly, a miracle, or are some of them relatively common while only one or two act as the genuine, severe bottlenecks in the Great Filter? The next generation of space telescopes, instruments far more powerful than anything we have today, will begin to provide the raw data we need to map these vast unknowns. They will allow us to test our models to see if the handful of nearby rocky, Earth-sized worlds we can study have the characteristics, like the atmospheric signatures of active volcanism or the presence of abundant water that our synthesis predicts are necessary for long-term habitability. The map of our inquiry is drawn, but the vast territory it depicts is still almost entirely unexplored. Let's apply this newly synthesized, multifaceted model to one final vivid walkthrough, a story of a world that had almost everything going for it. Imagine a planet, let's call it Planet C. It appears for its first few billion years to be a perfect success story. It is the right size in the right place with plenty of water. It has a large moon and a stable planetary system. Its internal engine is strong, driving both a protective magnetic field and a robust system of plate tectonics. Life begins in its oceans, and for 3 billion years its story almost perfectly mirrors that of Earth. Its geological thermostat works flawlessly, slowly drawing down atmospheric CO2 to compensate for the steady brightening of its parent star. Its early microbial life, like on Earth, discovers the magic of photosynthesis and begins to produce oxygen as a waste product. But on Planet C, this great oxidation event happens in a slightly different geological and chemical context. The specific chemistry of its oceans and continents leads to a different, ultimately fatal outcome. Instead of stabilizing at a level of around 20%, as it did on Earth, the oxygen level on Planet C continues to rise, unchecked. This triggers a series of runaway chemical reactions in the atmosphere that rapidly destroy other important greenhouse gases, particularly methane. The planet's delicate energy budget is thrown catastrophically out of balance. It rapidly, violently cools. The slow, patient, stabilizing feedback of the geological thermostat can't possibly keep up with the speed of the biologically driven chemical change. The planet tips, and tips hard, into a global, permanent ice age, a snowball state from which it can never recover. Planet C passed with flying colors through all the early, external filters, only to be undone billions of years into its life by a subtle, contingent, and ultimately lethal interaction between its own burgeoning biology and its planetary geology. It was a near success, a world that made it almost all the way, but a failure nonetheless. How can we possibly translate these immense, abstract, planetary-scale ideas into something practical, something that touches our own lives in a meaningful way? The key is not to try to solve the grand problems, but to practice seeing the underlying systems as they operate around you right now. You don't need a global climate model to do this. Simply notice the small, local, tangible feedback loops. Notice the way the morning sun strikes a window and warms a room, and how that warmth is stored and then slowly released by the materials in that room, the floor, the furniture, long after the sun has moved on. Notice the water cycle in your own garden, or even in a single houseplant, the intricate interplay of soil, roots, leaves, sun, and rain. By paying careful, gentle, non-judgmental attention to these small, testable, observable systems, you cultivate a mindset, a way of seeing the world that can then more easily grasp the larger ones. This is not about moralizing or prescribing solutions. It is about developing a new kind of attention, a new kind of quiet, observational agency. It is a local first framing. The fundamental principles of feedback, resilience, thresholds, and tipping points are not just abstract scientific concepts. They are operating right here, right now, in the room where you are, in the garden outside your window, in the body you inhabit. To see them and understand them here, on this intimate scale, is to begin to truly understand them everywhere. Where does this long and winding inquiry lead us in the future? We can imagine several plausible scenarios for how our understanding might evolve, and it's important that we label our confidence in each of them. It is highly probable, almost a certainty, that in the coming decades, our catalogues of known exoplanets will grow by tens of thousands, and we will have crude, low-resolution atmospheric data for many of them. This will give us a much better statistical understanding of how common Earth-sized temperate worlds are. It is plausible, but significantly less certain, that we will find what appear to be biosignatures, tantalizing chemical fingerprints like the simultaneous presence of oxygen and methane in the atmospheres of a small handful of these worlds. The interpretation of these faint signals will be incredibly difficult and likely contested for years. It is highly speculative, but not strictly impossible, that we might one day find evidence of technosignatures, signals, either atmospheric or electromagnetic, that could only be produced by an intelligent, technological civilization. But perhaps the most important open question is this: will we find a smooth continuum of worlds, some clearly dead, some perhaps marginally and microbially alive, some tantalizingly ambiguous, or will we find that planets are sharply and clearly divided into two distinct camps, the obviously and permanently dead, and a very, very few, like Earth, that are vibrantly, complexly, and unambiguously alive? The answer to that profound question will shape our understanding of our own place in the cosmos. For all the generations to come, how do we carry the emotional weight of this inquiry? An intellectual model of a cosmos that is potentially filled with the silent ghosts of failed worlds could feel bleak, lonely, or even terrifying. But there is another, perhaps more fruitful way to hold it. Let's attempt to reframe it emotionally. Imagine you are walking through a vast, ancient, old-growth forest. You are surrounded by towering, thousand-year-old trees, magnificent survivors that have weathered countless storms, droughts, and fires. But as you look around, you also see that for every one of these ancient living giants, the forest floor is littered with the fallen logs, decaying stumps, and the invisible ghosts of millions of seedlings that never reached the light. Does the overwhelming presence of all this failure, all this death, diminish the majesty and beauty of the surviving trees, or does it, in fact, profoundly enhance it? The fragility, the contingency, the sheer, breathtaking improbability of their long survival is precisely what makes them so awesome, so worthy of our reverence. Perhaps we can learn to view our own planet in this same way. The quiet, calm, non-anxious recognition of how many things could have gone wrong, how many critical junctures could have led to failure, can give rise to a profound, quiet, and deeply felt sense of gratitude and wonder for the astonishing fact that, at least here, at least for now, they went right. It is a perspective that replaces a sense of cosmic loneliness with a deep and abiding appreciation for the sheer, unrepeatable preciousness of this particular, improbable, tenacious, living world. We have reached a natural boundary in our exploration. We have followed the threads of data, theory, and models as far as they can coherently take us. We have built a plausible, internally consistent story of how a planet might survive, a story of feedback loops, contingent historical events, and the slow, synergistic integration of lifeless rock and living biology. But the data stops here. The next question, the one that naturally arises, the question of what it all means, is not one that science alone can ever answer. Does the staggering improbability of our own existence imply a purpose or a design? Or is it simply the inevitable result of the law of large numbers playing out across a vast, indifferent cosmos? Is our consciousness a bizarre and beautiful fluke, or an intended, convergent outcome of the universe's fundamental laws? These are not scientific questions. They are deeply philosophical and personal ones. Our journey tonight was designed, in part, to bring us respectfully to this boundary, to walk right up to the very edge of what can be known through observation, measurement, and inference. And here, at this quiet edge, we must have the humility and the wisdom to hold the questions open. There are no easy verdicts to be found here, only a quiet, protected space for reflection, a place where the methodical work of science gracefully ends and the personal work of meaning-making begins. Let's hold two final, powerful frames side by side, not as competitors, but as complementary ways of seeing. One is the anthropic frame, or the anthropic principle, In its simplest form, it suggests that the universe must, by definition, have the properties we observe, because if it had substantially different properties, we wouldn't be here as conscious observers to ponder it. In this view, our own existence acts as a powerful selection effect, filtering our perception of reality. It is, in a way, a perfect tautology. We see the universe we see because it's the only kind of universe that can produce observers like us. But it is a profound and useful tautology. The other frame is that of emergence. In this view, the properties of the universe are simply what they are, and fantastically complex phenomena like life and consciousness are simply emergent properties that arise, perhaps inevitably, when the right ingredients and conditions are present for a long enough time. They are not the preordained goal of the universe, but an interesting, beautiful, and perhaps very common consequence of its fundamental physical laws playing out over billions of years of cosmic history. One frame can feel like it points toward some form of design or purpose. The other points more toward chance and physical necessity. But both can and perhaps should be held with the same deep sense of humility. Both, in their own way, acknowledge the apparent and astonishing fine-tuning of the cosmos that allows for our existence. Whether that fine-tuning is a clue to a deeper, hidden purpose, or simply the result of a cosmic lottery that we happen to win, is a question that sits far beyond the horizon of our current knowledge. We can let them exist together, two different languages for expressing the same fundamental, humbling awe. And so with that we arrive back exactly where we started, in a quiet room at the end of a long day. But perhaps we arrive with a different, richer sense of our place in the world. You are in a room, on a planet that is spinning at 1,000 miles an hour, held in a stable, predictable orbit by the gravity of its star and the gentle, stabilizing tug of its oversized moon. You are breathing an atmosphere that was painstakingly built in large part by microbial life over the course of 3 billion years. You are, in every sense of the word, a part of a system, a living, breathing link in a 4.5 billion year long chain of improbable survival that stretches all the way back to the cooling of the Earth's primordial crust. Your own body, the very atoms that make up your bones and your blood, contains the same heavy elements forged in the hearts of long-dead stars that also make up the rocks and the water of this world. This is not a poetic flourish. It is a literal, physical, chemical truth. To feel your own aliveness, the quiet, steady thrum of your own metabolic engine, is to feel your deep and unbreakable belonging within this immense, ancient, and resilient system. You are in the loop. The sense of agency this provides is not about controlling the planet, but about recognizing with gratitude and wonder your profound and intimate connection to it, your brief but meaningful participation in its ongoing story. Let's briefly, gently retrace the long path of our steps tonight. We began with a single, simple, quiet question. What if our world is one of many that tried, and the only one nearby that managed to survive? We set aside the demand for certainty in favor of a commitment to methodical, patient curiosity. We grounded ourselves in the physical reality of the present moment, then zoomed out to explore the vast, intricate machinery of the planet. We followed multiple evidence tracks through geology, astronomy, and biology, examining the complex web of feedback loops and the crucial external conditions that have kept Earth stable for so long. We fairly and honestly considered the powerful objections to this view, the idea that Earth may be exceptionally rare rather than exceptionally resilient. We then executed a crucial turn, reframing the question from a simple, unhelpful binary to a more nuanced continuum of habitability, a long and arduous series of great filters that any aspiring living world must pass through. We synthesized these disparate ideas into a minimal, coherent model of long-term success, all while acknowledging the deep and profound uncertainties that still remain. And finally, we brought this vast, cosmic perspective back to an emotional, philosophical, and personal level, arriving at the quiet boundary where science gives way to meaning. And so we ask the core question one last time, now with a new richness, a new texture, a new depth. What does it mean to live on a world that has, against all conceivable odds, held on? As our shared journey for this evening comes to its natural close, there is a moment for a quiet, unspoken form of community. Thank you for being here tonight. Thank you for lending your most precious resources, your time, your attention, your curiosity, to this shared exploration. In a world so often filled with noise, speed, and urgency, the simple, deliberate act of setting aside time for quiet, methodical wonder is a profound and restorative one. There is no call to action here, no imperative to follow, no task to complete. The invitation is simply to carry the spirit of this inquiry with you, if you so choose. If this exploration has been meaningful to you, perhaps you will share it with someone else who might appreciate a moment of calm, structured curiosity. But that is entirely optional. The most important thing is the sense of quiet connection we've cultivated to the ideas, to the planet, and to the silent, invisible community of other listeners, each in their own quiet space, all wandering together under the same vast sky. The intellectual tension of our inquiry can now be gently and completely released. We have not arrived at a final, definitive answer, because there is no final answer to be had. Instead, we have arrived at a state of enriched, peaceful curiosity. The goal was never to solve the great mystery of our existence, but to appreciate its depth, its texture, and its profound improbability more fully. The grand questions we've held together tonight can now be allowed to soften, to become less like problems that demand a solution and more like quiet, thoughtful companions for our own private, reflective moments. Does the universe teem with life, or is it mostly achingly silent? Is our world a common template or a bizarre and beautiful anomaly? These questions will remain. They will continue to echo long after the sound of my voice has faded completely. Let them live on within you, not as a source of anxiety or existential dread, but as a perpetual source of deep and humbling wonder. The most beautiful and sustainable state, perhaps, is not in knowing all the answers, but in remaining fully, peacefully, and perpetually alive to the questions. Let stillness be the final word, not a verdict. And so we end precisely where we began, in a quiet room, with the gentle, steady, autonomous rhythm of your own breath. Become aware, one last time, of the air around you, the way it touches your skin. This specific, life-giving mixture of nitrogen and oxygen and argon is the accumulated result of a 4.5 billion-year conversation between rock, ocean, and life. Feel the gentle, constant pull of gravity, a reassuring, anchoring pressure. That is the silent, omnipresent signal of a planet massive enough to hold on to its precious atmosphere, a planet strong enough to keep you anchored safely to its surface. In the deep silence, if you listen carefully, you can almost feel the slow, silent, steady spin of the world beneath you, a rotation that was stabilized into predictability by a long-dead cosmic collision that formed our moon eons ago. This single, grounded sensory moment right here, right now, contains the full echo of everything we have explored together tonight. The micro reflects the macro. Your quiet, stable, breathing presence in this room is a direct testament to the improbable, resilient, and 4 billion-year-long journey of your world. And in that quiet, deeply felt recognition, perhaps you can find a genuine and abiding peace as you let go of the day and drift gently now into a well-deserved sleep.